All right, so I've gone through and shown you a lot with chemical reactions. The very last thing we're going to do with this particular unit is work between different quantities of a substance. So one of the reasons that we include this in this part of the unit is because part of balancing and creating chemical reactions is to figure out roughly how much product I'm going to get from a reaction. So let's say I wanted to make 25 grams of a substance, I don't know, some type of medicine. Well, I need to think about what types of chemicals I need to start off with in order to get 25 grams of each substance. How much of chemical A and how much of chemical B do I need to react together in order to get the 25 grams of product? So we use a fancy chemistry math and a balanced chemical equation in order to figure that out. If we really break down this beautiful diamond that's over here, let's say you end up with a half-carat diamond for one reason or another, it has 5.0 times 10 to the 21st carbon atoms. Well, how do I figure out how much starting materials I need to synthetically grow a lab diamond that is half a carat? I need that many carbon atoms. So I need to find some way to harvest those carbon atoms or utilize that many carbon atoms in a chemical equation in order to produce my lab diamond that's shown over here. So one of the ways that we do this is by what is known as formula mass, or sometimes this will be referred to as molar mass. Now, we've already done this before when we've looked at average atomic mass or atomic weight. It is the masses, or the sum of all the atomic masses of all atoms that are in the compound, and we use the masses that are found on the periodic table. So for example, NaF, we take the molar mass of Na, which is 22.99, and the molar mass of fluorine, which is 19, and add them together to get our AMU value. It's just in this instance, it's how many grams are in a mole of something. We'll talk about a mole here in just a minute. But notice that when I have more than one element in my compound, I need to take that into consideration when I go through and calculate the molar mass. So H2O, 2 hydrogens and 1 oxygen. So notice we multiply the molar mass of hydrogen by 2. When we're dealing with something like NH4, 2, CrO4, that 2, remember it's distributive property of math, that 2 distributes to the nitrogen. 2 H4s is 8 hydrogens, 1 chromium and 4 oxygens. So you see that in the equation that's calculated the molar mass of that. And then barium nitrate, we need 1 barium, 2 nitrogens, and 6 oxygens to go through and calculate those. So I would expect that you know how to do the exact same thing. So pause the video, work through these molar masses, and we'll move on here in just a moment. All right, so same thing that we've done previously, should be no issues here. We have 1 calcium and 2 bromines, so 1 calcium, 40.08. Again, that is based off of the information that is on the periodic table. We have 2 bromines, each at 79.90. We're going to multiply them and add them together. You might hear my neighbor mowing their lawn in the background because that's what they do. We end up with 199.88. And the unit we're going to start using for this is grams per mole. Sorry, mole. M-O-L. There you go. AlNO3, remember that's distributive property of math there. So we have 1 aluminum, 3 nitrogens, and 9 oxygens. So 1 aluminum at 26.98. 3 nitrogens at 14.01. And 9 oxygens at 16. And we just simply plug those into our calculator and solve. And we end up with 213.01 grams per mole. Okay, so again, just straightforward there. We've done this before. We'll continue to do this again moving forward.